Imagine this. It's early morning, you're on the runway, it's stretching out like a silver ribbon, you hear that faint whine, turbines spooling up, feel it vibrate right through you, and that smell, sharp, clean jet fuel in the air. Then the voice in your headset, calm, clear. You are cleared for takeoff. You push the throttle forward, engines roar, this deep rumble right in your chest. The ground trembles, the aircraft surges ahead, faster, faster, and then somehow the earth just falls away. You're not bound to the ground anymore, you are flying. And in that incredible moment, you're not just a passenger. You are the mind behind the machine. That's the world, that exhilarating feeling we're diving into today. Not just watching, but really understanding it like the engineers of flight. Welcome.
It really is an amazing world. And today, yeah, we're looking into the source material from this Zero to Hero in Aeronautical Engineering course. It's totally free, audio only, which is interesting. And it's built for students, maybe just finishing 12th grade, who dream of this stuff. Takes you from, well, zero, the absolute basics, right up to professional principles.
So it's a full pathway, essentially,
Huh.
mastering the science and I guess the art of flight from scratch.
Exactly.
Okay, so for this deep dive, our mission is to really get under the hood. What is aeronautical engineering? Beyond just a definition, we want to map out the whole landscape for you, show you the full roadmap, and figure out how you learn this complex stuff effectively, especially in an audio-only format. And, maybe most importantly, start thinking like an engineer. You know, curious, precise, creative.
That's the goal.
All right, let's find your wings. So first big question, what is aeronautical engineering? Textbooks say it's the branch of engineering dealing with design, development, testing, production of aircraft within Earth's atmosphere. Sounds straightforward, but I bet there's a lot more packed in there, isn't there?
Oh, absolutely. I mean, that definition is correct technically, but it doesn't capture the real magic of it.
Right.
At its heart, aeronautical engineering is, well, it's about mastering the invisible.
Mastering the invisible. Okay, tell me more.
Think about it. You're dealing with air, with forces, energy, things you can't see, can't touch, yet you have to understand them, predict how they'll behave with incredible accuracy. The real challenge, the art, is bending those unseen elements so that a machine, often a very heavy machine, can lift off, fly around, land safely every single time.
Right, making the unseen predictable, controllable.
Exactly. That's where the difficulty and the fascination lies.
That's a really powerful way to think about it. It makes you appreciate just how many things have to work perfectly. So what are the specific disciplines or fields of knowledge someone needs to tap into for that, to master these invisible forces?
It's definitely a blend, a powerful mix of several key areas. Each one is critical. You absolutely need physics. That's foundational for understanding how forces act on something moving. The push, the pull, resistance, all of it.
Okay, physics. Makes sense.
Then mathematics. It's the language you use to quantify everything, to model it, predict it. Precision matters hugely here.
Right. Can't guess with an airplane.
Definitely not. Then there's material science, choosing what the aircraft is made of. That's huge. Finding that balance, often tricky, between being super strong and super light.
That's strength to weight ratio.
Precisely. And finally, systems engineering. This is about making sure all thousands of parts, tiny bolts to complex electronics, work together perfectly as one unit.
Wow. Okay. So it's not just one thing.
No, and underlying all of it, fundamentally, it's about problem solving. Because in aerospace, honestly, every gram counts. Every degree matters, every millisecond. That level of precision isn't just like nice to have. It's absolutely essential for safety, for performance. So you need that holistic view, understanding how all these fields connect to really see the whole system.
That really clarifies how interconnected it all is. It's not just isolated subjects. Okay, so to give you listening a better sense of how this knowledge builds, let's look at the flight plan from the course, the roadmap. It's a journey structured through 9 main modules. Gives you a real sense of the scope, the detail involved. We start with Module A, Orientation and Math Physics Backbone. This isn't just learning definitions. It's about learning to think in terms of vectors, forces, energy. Getting the engineering mindset for systems, and crucially, no heavy math equations thrown at you right away, just the concepts in plain language, building that toolkit.
Yeah, you need the right tools before you build anything complex.
Yeah.
Laying that solid groundwork first.
Exactly. Then you move into Module B, Fluid Mechanics Foundations. Here you start getting into the nature of air itself, how it flows, pressure, how we predict, and control its movement.
Understanding the medium you're flying through.
Right. And then it gets really cool with Module C, Aerodynamics. This is the magic, isn't it? How a wing actually generates lift, how shape, speed, air pressure interact, and how it changes dramatically from a slow glider to a supersonic jet or even, hypersonic flight.
The rules change depending on speed and altitude. It's fascinating.
After understanding the air, we hit Module D aircraft structures and materials. How do you build something so light, yet strong enough? Strong enough to handle incredible forces, temperatures, vibrations.
That engineering challenge again. Lightweight and robust.
Then Module E, flight mechanics, stability and control. This covers how aircraft actually move, how they stay stable, especially in, say, turbulence, and how pilots or autopilots control them with such fine precision, landing a huge plane on a narrow strip.
That whole dynamic system, and of course you need thrust. So Module F propulsion, this covers the engines. Everything from propellers to jets, even rockets, how they turn fuel into that massive push forward.
Overcoming drag, reaching speed, got it.
Yep.
Okay, then Module G, avionics, systems and operations, sounds like the brains and nerves.
Pretty much, it's the nervous system. Avionics, the electronics, instruments, navigation, communication, plus all the other systems. Life support, hydraulics, electrical power, keeping everything running.
Wow, okay. Then Module H, design, testing and certification. Taking an idea, a drawing, all the way to a certified flying machine that meets incredibly strict global standards.
A huge process. Rigorous testing is key there.
And finally, Module I, special topics and case studies. What's in there?
That's where you explore things like drones, hypersonics, maybe look at specific programs like in India. And really importantly, it focuses on how to keep learning. This field changes fast. So this whole roadmap, it's not just a list. It shows that logical buildup of knowledge. And yeah, the huge scope of what you can actually master.
That is quite a journey laid out. And thinking about the course being audio only, that adds an interesting twist. No diagrams on a screen. You're building these complex pictures, these diagrams, right in your own mind. That sounds challenging, but also maybe a really powerful way to learn, to internalize it.
It absolutely is. And it's doable. We have practical strategies for you. First, really consciously pause and picture. When you hear a description, say, of an airfoil shape or an engine layout, stop for a second. Actively imagine it in 3D.
Okay, use your mind's eye.
Exactly.
Yeah.
Second, use analogies. If the course says something like, air acts like invisible honey at low speeds, try to feel that imagined stickiness, how it might resist motion.
Make it tangible in your head.
Right. Third, rehearse mentally. Don't just listen passively. Repeat key ideas back to yourself in your own words. That active processing really helps lock it in.
Okay, and fourth.
Fourth, keep a learning journal. Sounds low-tech, but sketch what you're imagining. Even rough drawings. Getting those mental models down on paper, even imperfectly, helps solidify them. Makes the invisible visible to you.
Those sound like great tips not just for this, but for learning almost anything complex.
They really are. They're techniques for deep learning. You're not just receiving info, you're actively constructing the knowledge yourself.
Which is much more effective in the long run.
Definitely. Building those strong internal models.
Now, beyond the knowledge and the learning techniques, you mentioned earlier that success in engineering requires a specific mindset. It's not just formulas, it's how you approach problems, right? Especially when things get tricky. What are those key traits?
Yeah, that's crucial. The mindset is just as important as the knowledge. Several things stand out. First, you absolutely need to be curious. Always be asking why. Why does this work? Why this material? Why that shape? Constantly questioning drives understanding and innovation.
Okay, curiosity. What else?
Second, be precise. We keep coming back to this, but it's fundamental in aerospace.
Yeah.
Small errors can have, huge consequences. Detail matters. It's about safety, efficiency, lives.
Right. Precision is non-negotiable.
Third, be patient. You won't master this overnight. It takes time, persistence. You'll hit roadblocks. Keep working at it.
It's a marathon, not a sprint.
Exactly. And fourth, be creative. Engineering isn't just applying rules from a book. It's often an art, finding innovative solutions, solving problems nobody has solved before.
That blend of science and art again.
Precisely, you're inventing new ways forward.
I can really see how cultivating those traits, curiosity, precision, patience, creativity, develops critical thinking. Skills usable way beyond just engineering.
Absolutely. It changes how you approach any challenge.
To make this feel more real, let's talk about someone who embodied that journey. APJ Abdul Kalam. Before becoming India's missile man, eventually president, he was just a boy in Ramaswaram. Loved watching birds fly, dreamed of it himself, studied physics, then aerospace engineering, worked on India's very first satellite launch vehicle. It's quite a story.
Yeah, and what's really inspiring there, what's fascinating is it shows you don't need to be born into this field. You don't need some special background. You can absolutely grow into it.
Mhm.
His story is a testament to the power of passion, sheer dedication, focused learning for
Mm.
anyone, really, regardless of where you start.
That's a powerful message. Commitment can take you amazing places. And speaking of beginnings, those first steps,
Mm.
let's wrap up with a fun fact that really puts the whole history of flight into perspective. Okay, get this. The very first powered flight, Wright brothers, 1903. It lasted just 12 seconds
12 seconds.
and covered only 37 meters. That's it.
It's amazing when you think about it. That 37 meters,
Right.
that's shorter than the wingspan of a Boeing 747.
Wow, really? Shorter than the wingspan.
Yeah. Yet that tiny hop, that 12 seconds, it changed everything. Changed human history forever.
Incredible.
It just shows how huge things can come from small, even hesitant beginnings, if the ingenuity and the drive are there.
Proof that you have to start somewhere, even the biggest journeys. Okay, so let's bring this all together. What does this deep dive mean for you listening right now?
Well, first, you've hopefully got a much clearer gut-level feel for what aeronautical engineering really is, beyond the textbook stuff, in plain language.
Understanding that mastering the invisible concept.
Exactly. Second, you've seen the roadmap, the full flight plan for exploring this field, module by module. You know the territory now. The structure of the journey.
Third, you've got practical strategies for how to learn this, even without visuals. Building those diagrams in your mind, actively learning.
Using imagination, analogies, rehearsal, sketching.
Right. And fourth, you understand that crucial engineer's mindset, that need for curiosity, precision, patience, and creativity.
Yeah, the mindset that fuels success.
So it's about seeing the path and having the tools and the mindset for the journey.
Exactly, equipping yourself intellectually and mentally.
All right, now for you, your first design challenge, an imagination exercise. Close your eyes for a second. Seriously. Imagine you have to design a paper airplane. But here's the goal. It has to fly the entire length of your school's football field. Now think like an engineer. Don't just picture it. What shape would you choose? Wings. Body. How would you make it stable? To fly straight and far, not just tumble. What would you change if you knew there was a strong crosswind blowing? Think about it. If you're doing that, you've just taken your first step, applying these ideas.
And that raises a really important question, doesn't it? How do you take a problem like that, even a simple paper plane, and break it down? Break it into smaller, solvable parts. That instinct, that methodical approach, it's engineering right there.
Fantastic first step. So next time, for those ready to go dipper, the journey really kicks off. We'll get into the absolute fundamentals, the language of motion, vectors, reference frames, and units, the bedrock for everything else in aeronautics.
Essential starting point.
You've just completed your first flight with us into aeronautical engineering. Keep that curiosity fired up. Keep asking why, and we'll see you for your next deep dive.